we're going on. We've been doing what I call general relativity. General relativity is the theory of gravity. It's very much like Newtonian gravity, except when the fields get really, really strong. When do they get really strong? When the energy involved is comparable to mc squared. Now, that actually happens in a black hole. There's an equation I didn't really give you. Let me just state it. You don't have to know it. For the energy, if you have two objects, and they're close to each other, this has little m, this has big M, then it takes energy to pull them apart. And the equation for that is related to the fact that there's a force. The force is strong. You've got to overcome that force. You have to put work in to pull them apart. So we call this the binding energy, the energy it takes to pull them apart. If the binding energy is great, well, the binding energy for gravity, called the binding energy, that's the energy to pull apart. And the equation for this in gravity is that this is equal to the gravitational constant times the first mass times the second mass divided by the distance between them. That's the equation. So that's the binding energy. Now, if the binding energy of this thing being bound to that, suppose that binding energy is equal to the energy of the particle, mc squared. That would take a really strong gravitational field for that to be the case. But such things do exist. They're called black holes. Things where if you were to take all of the energy, all 100% of the energy intrinsic in this particle, and just try to use that to escape, it wouldn't be enough, because this is equal to the binding energy. That's when you have a black hole. Previously, I explained a black hole as what you get when the escape velocity is equal to the velocity of light. This is a deeper understanding of the black hole. It says the energy to take it out is more than the energy it has, even if you converted all of its mass into energy. Well, you can give it more energy then, right? Can't you give it more energy? Yeah, but if you give it more energy, you're giving it more mass. You can't win. You can't get out, because there's no way you can have more energy if this equation is satisfied. Now, let me just take a look at this equation. And what I can do is rewrite it. Well, the m's cancel, you notice. And so we get that it's a black hole if gm over rc squared, if this is bigger than that, if this is bigger than 1. This is the equation of a black hole. It's the equation. It only has m in here. It doesn't matter what you put here, because if you put something here that has more mass, it's more tightly held to the star. So it doesn't matter what this is. It only matters what this is. The equation for the black hole actually has a 2 in here, and that's only because the radius is defined in a funny way. But that's the equation for a black hole. And if your mass is big or your radius is small, you can't get out, because any attempt to give it energy increases its mass and therefore increases how tightly it's held to the black hole. And so you can't win. This is a deeper understanding of black hole than you will get from any of the popular literature, which talks about escape velocity as being equal to the speed of light. That may not make intuitive sense to you. But this does. You see, the black hole is a natural consequence of the fact that energy and mass are so closely related. You can't give something energy without giving it mass. And if you give it mass, it's more tightly bound. So the fact that black holes existed, back when I started teaching here at Berkeley, I used to speculate that maybe there was black holes in this particular location where a star had blown up. See, one of the things that can happen is when a star blows up, the center of the star collapses into a black hole. And there's some speculation about that. There still is. Things in the sky called Cygnus X1, for example, are almost certainly black holes. But just in the last 10 or 15 years, we've recognized that black holes are actually very abundant. And I'm going to be talking more about this very shortly, but since I'm on black holes right now, let me just state that when you look up in the sky from the Earth, you look up in various directions and you see these stars. And in fact, all the stars you can see with your unaided eye, almost all the stars you can see, the individual stars, are really very close stars. That's why you see them. And so they seem to be everywhere. Everywhere you look, every direction you look, here are these stars. But you're only looking at close things. It's like if you were now to look around and say, where are Cal students? And you look around and say, oh, there's one there, there's one there, and there's one there, and there's one there. And they seem to be all around me. And unless for a few people on the edge, they're only on one side. But for most people here, you're just surrounded by other Cal students. And you get the impression that Cal students are everywhere. But you're only looking at the close ones, and you can't see a mile away. So you don't know what's out. Well, you do know what's out there, but just from looking, you wouldn't. Well, mostly what we see at night are these nearby stars. There aren't that many of them that you can see. You say millions and millions. No, you can't see millions of stars. You see a few thousand. That's it on a clear night. Just looks like millions. But try counting them. Take a little region of the sky and say, how many stars are in there? I say 1, 2, 3, 4, 5, 5, 6. Now, how many of those regions are there? Oh, there might be 1,000. Okay, so that makes 5,000 stars. Not that many. Not like the grains of sand. A lot of stars you don't see. Now, with a telescope, you can see them because you have a big mirror. It gathers light. You can see these dim stars. Why are they dim? Because they're far away. And when you study this, what you discover is the stars are not uniformly distributed, but seem to be in a disk, like a plate. They're in a big disk, like this. And we're in this part of the disk, and you only see the nearby stars except with the telescope. With the telescope, you look up this way, and you find you run out of stars. You look down this way, you run out of stars. You look this way, and you see lots of stars. And you look this way, and you see lots of stars. So we know we're in this relatively flat plate. I was trying to see if I have anything here that looks like a flat plate. And with a telescope, you realize that. Now, when you look in this direction, you see zillions of stars, and then you recognize that, oh, I can see that with my unaided eye. When you go out at night, you can't do it at Berkeley because your eyes just, it's just the sky, the air is too bright from reflected street lights. But if you go out into the mountains, if you look off in this direction, you won't be able to see individual stars because they're too far away, but you find sort of a hazy glow in the sky from all these distant stars that are this way, and even this way, you find this hazy glow. And you look at it, you realize you're in the middle of a plate, and there's that hazy glow making its way all the way around. It looks sort of milky, and traditionally it's been called the Milky Way. And that's what you're seeing, these distant stars. If you get a good pair of binoculars with big lenses and you look at this, you'll discover you do see lots of stars. You see lots of little stars because you'll see these over here and there aren't any up here or down here. So with a pair of binoculars looking at the Milky Way, you'll be amazed at all these little dots that appear that you saw with your unaided eye as just a big milky patch that goes all the way around. That is the plane, that is the plate, the disk of the Milky Way. Now, some people don't like the word Milky Way. They say that's a common name. This is referred to as, technically, in the scientific literature, it's referred to as the galaxy. Now, we happen to know now that there are other galaxies, so those are called galaxies. The other ones with little g. It's sort of like people who believe in one God will capitalize the G and refer to everybody else's gods with a lowercase g. The galaxy, the scientific name for what we commonly call the Milky Way, is the official name. Anybody here speak Greek? Anybody know what the word galaxy means in Greek? Nobody? It's kind of cute. It means milk. So the scientific name for the Milky Way, so you don't have to use this common name, Milky Way, is sort of Milky Way in Greek. I think I related to you a similar thing happened with tidal waves. Scientists a few decades ago decided they didn't like the term tidal waves because tidal waves have nothing to do with tides, which is wrong, of course. They really do have things to do with tides, but they decided that this is misleading, so they decided to call them tsunamis. Not tidal waves. Tidal waves are misleading. You think they have something to do with tides. They call them tsunamis, not knowing or not appreciating that the Japanese word tsunami means harbor wave. So now when a tsunami comes in, you won't be misled into thinking it has anything to do with the moon and tides, but you think, what's this big harbor coming in? Anyway, somehow if you make a word foreign, it becomes scientifically okay. And I think that's kind of silly, but that's what we do. So this is the galaxy. And it turns out this big disk is spinning. It's held together by its own gravity. That is, there are more stars in the middle here. There's even a big bulge in the middle. And this thing looks like a big sombrero, and the whole thing, a double-sided sombrero, and this whole thing is spinning, and you think the centrifugal force would make us fly out, but there's so much gravity from all these stars inside that it holds us together. So every star you see at night, on the unaided eye, almost, I'll give you an exception in just a moment, is part of the galaxy. The galaxy is spinning, and now we know, thanks to a discovery actually made by Professor Charlie Townes, inventor of the laser. When he got tired of lasers, he went into astrophysics and discovered, I think he, probably more than anybody else, presented the evidence that really compelled people to believe and to understand that at the center of the Milky Way galaxy, there is an enormous black hole. We don't yet know why. It's not equal to the mass of a sun. It's probably equal to the mass of maybe many millions of suns. Why is there a black hole there? It probably had some role or was an artifact of the creation of the galaxy. Why does the galaxy exist? Why do we have this disk of stars? People are trying to understand this. We'll be talking more about this in the coming lectures. But it is an enormous black hole. Now, I said I wanted to correct myself when I said these are the only stars you can see at night. Not quite true. If you go up in this direction, there's another galaxy consisting of typically 10 billion stars. And we call it the Andromeda galaxy. And it's way off over there, but you can see it. And if you look, it's in the constellation Andromeda. And the constellation Andromeda means there are a bunch of stars here, right there, that ancients decided, not that they really looked like the Queen Andromeda, but I believe that they made up a story that if you look at this, you can see the queen in her chair, and that this was actually an aid to memory. That the ancients would teach the children that those stars are Andromeda. They even make up a legend and stories about this. And the real value of this was to help the child remember and recognize that star so they could tell what time it was at night and where they were. A lot of people say they thought it looked like Andromeda. I don't believe that. The Greeks were experts at memory. They had memory tricks. You people should learn memory tricks. They will help you memorize things. And one of their memory tricks was to make up stories associated with stars so the kids could remember it. And if you look up in the direction of the constellation of Andromeda, this little fuzzy patch there, and that fuzzy patch is its own Milky Way. We have our Milky Way, we're in the middle of it, but outside of it there's this other Milky Way. I'll show a picture of Andromeda maybe later today on my computer. But Andromeda also has a black hole in its core, a big black hole. We now believe that most of these aren't the only two so-called galaxies. As I'll be showing shortly, if you look out at different directions with a powerful enough telescope, you find lots of galaxies. Now, our own Milky Way has something like 5 to 10 billion stars. That's a lot of stars. The sun is sort of a typical star, maybe a little bit dim on average compared to the other stars. But there are about 10 billion stars in our own galaxy. There's a comparable number, maybe a little bit bigger, in the Andromeda galaxy. And as we look, some galaxies are smaller. There's a little galaxy sitting here very close to us That's called the Large Magellanic Cloud. It was discovered by Magellan. What I mean by discovered, of course, was well known to all the people who lived in South America, but Western civilization was unaware of it because you can't see it from the northern hemisphere. So when he was the first one to go to the southern hemisphere and report back that there were constellations completely unknown to the northerners, and he was able to give them names. And there was this fuzzy patch called the Large Magellanic Cloud, which we now know is a small galaxy. It's like a satellite galaxy. It's like a moon. The moon goes around the Earth. This Large Magellanic Cloud goes around the Milky Way. And it's quite a bit smaller. Go down to below the equator, make a point of seeing it. This little patch that's there. I went down there in 1987. I went down to Chile because a supernova, an exploding star, went off in the Large Magellanic Cloud. It was the first bright nearby supernova to go off in our vicinity in 400 years. So I went down to Chile to observe it, and we made measurements on it, looking for a pulsar within it. That was my first trip below the equator, 1987. I don't know whether the Large Magellanic Cloud has a black hole in it or not. I'm not sure whether it's known. But these black holes exist. They have some role. It's not enough gravity to be really important in holding the galaxy together. But there are lots of things in the galaxy we don't fully understand, including their formation, although there are some nice simulations now that give us some speculative theories about how these clumps of stars might have formed. And we'll be talking about that on Thursday and maybe next Tuesday. Once again, homework is due tonight, but not next Tuesday. This is your last homework, so do a good job. It should be either a newspaper article or read one of my essays. That's black holes, and I think that's about all I'm going to say about black holes right now. Any other questions? We talked before class about black hole evaporation. A black hole has a strong gravitational field outside of it, and according to modern theory, the energy of the black hole is part of that field. And so if that field, which is outside of the black hole, emits particles out, something called Hawking radiation, because it was Stephen Hawking who first really used the equations of quantum mechanics to demonstrate how this could be happening. Hawking radiation. With Hawking radiation, because some energy is lost with the particle leaving, not from inside the black hole, but from the field outside of the black hole, that reduces the mass of the black hole. It's almost as if things can't get out, but the black hole can lose energy. In fact, small black holes can lose this so rapidly that if you have a tiny black hole, it probably will disappear. All of its energy will be lost from its gravitational field. It loses mass. Nothing from inside gets out, and yet what's inside disappears. How can it disappear? Well, there's a way of thinking about this. If you have, let's say, a proton inside the black hole, and here, in the field outside of the black hole, this intense gravitational field becomes so strong that out of the vacuum, it creates a proton and an antiproton. Antiproton usually done with a bar over it to indicate it's an antiproton. In the strong gravitational field, there's so much energy that it can momentarily create this. Now, if this proton goes flying out, at the same time this antiproton goes in, the antiproton can annihilate this proton. And in the end, you have a net energy release. So even though nothing technically came out of the black hole, you are annihilating the stuff that's inside of the black hole. The energy is going into this proton and a decrease in the gravitational field. It's a really weird mechanism. It raises issues that we have only begun to touch upon, interpretations of the uncertainty principle, and what does negative energy mean, and things like that. But Hawking came up with this. This was really Stephen Hawking's major claim to fame. It was a fundamental breakthrough. It was one of the first steps in understanding the relationship between gravity and quantum mechanics. He went on to discuss black hole entropy, which is, again, a subject that gets kind of technical, and I'm not going to go into in any detail. But Hawking radiation says that black holes can evaporate. Now, if you work out the equations, really tiny black holes, I mean, suppose I had a black hole right here. it would evaporate very quickly, a tiny little black hole. Little black holes don't have to have much energy. They just have very, very dense mass. They don't have to have much energy. You could imagine that maybe in principle an electron is some sort of a black hole because it doesn't have a measurable diameter. Why doesn't it evaporate? Because it has electric charge. And electric charge, there's no way to get rid of it. But mass is energy, and you can get rid of that. So this is called evaporation. Large black holes, like in the center of the galaxy, you calculate the amount of evaporation, and it is completely negligible. So that's not going to disappear. Why do you need to know this as a future president? You don't. We're beyond that now. We're not doing future president stuff anymore. We're doing kind of neat stuff. Some of you, this is what you really wanted all along. Not everybody came here because they want to be ready in case they're ever drafted to be president of the U.S. or of a major company. But some people, this is the physics that really intrigues them. And so we're winding up the semester with this unneeded to know physics. Black holes, Hawking radiation. So this is the tie-in between quantum mechanics and gravity. It's called Hawking radiation. It says that black holes can evaporate. At most, you might get a multiple choice question. What is Hawking radiation? A, B, C, D, E. One question answer would be evaporation of black holes. That would be the right answer. But I'm not going to ask you to write an essay on this stuff. There are too many conceptual issues here that we don't have time to talk about. So I'm not going to ask you to try to put that all together in your head. You're not supposed to feel comfortable with this. Instead, I'm just triggering you to want to continue to read about this stuff for the rest of your lives. Let me talk a little bit more about, we're getting to elements here where subparticle physics, really what's going on in atoms and nuclei, relates to what's going on in the universe. And there are a couple points that have held off till the end. We've discussed quarks in the past. They came up. I said what the proton is made out of. But now that we've done a little bit of quantum mechanics, I want to discuss two items. One of them is quarks, and the other is exchange forces. We'll begin with exchange forces. And then we'll do quarks and confinement. Again, I apologize. I don't really think you need to know this. But you'll come across it because it'll be in newspaper articles. Exchange forces come from a study of quantum mechanics, the equations of quantum mechanics, and attempts to solve them in approximate ways. And in doing this, they developed something called perturbation theory. You don't have to know that word. Perturbation theory was a method of taking the equations of quantum mechanics and in cases where you couldn't solve them exactly because things were too complicated, you can make some very good approximations and solve it as a perturbation. For those of you who have studied calculus, this is like a Taylor series, but for the quantum mechanics equations. And so you get a series of terms in this. Now, some people looking at these series of terms, particularly Feynman, recognize that these terms could be interpreted in a physical way. It wasn't just pure math. This actually made some sense. So his interpretation was the following. And he followed up on this and said, maybe this interpretation is more fundamental than the equations. So this was Richard Feynman. One of the most creative theoretical physicists of the 20th century. He became famous for a role he played in the Challenger disaster when he brought in some seals and showed how badly they work when they get cold, and this turned out to be the reason for that the Challenger accident killing astronauts occurred. Feynman, of course, didn't come up with that idea himself. It was presented to him by NASA engineers, but it made him famous. He never said he liked fame. He would have turned down his Nobel Prize, he said, except that would have given him more fame than accepting the Nobel Prize. So he had these awkward problems. A fascinating person, and one of my favorite books is a book that he wrote called Surely You're Joking, Mr. Feynman. You want to give someone a physics book that they'll really like. The title comes from an incident that he describes early in the book, in which he's a student and he's at some dean's party, and I think the dean's wife asks him if he would like something, and he gives this completely inappropriate, nerdy, geek-like answer, and she says, "Surely you're joking, Mr. Feynman." Anyway, who here has read the book? I'm just curious. Okay, it's a great book. You'll love it. You'll love it. Your parents will love it. Your friends will love it. Everybody will love it. It's just a really humorous book, gets into the personality of Richard Feynman. But his insight was that if you look at these equations, you could understand them in the following way. Normally we think of an electron, and here's another electron, and they repel each other. We know that. How does that happen? Well, this electron creates an electric field, E. And this electric field here, this electron, because it has a charge, it feels the electric field. And that pushes it away. Now, we know that waves are waving fields. What about fields that aren't waving, that are just static? From looking at quantum mechanics, Feynman realized the equations could be interpreted as what's really going on here is not some mysterious field, but little particles, little waves of electromagnetism are constantly in motion around here. And these little waves of electromagnetism wind up giving you the effective field. This dropped out of the quantum mechanics equations. It seems absurd, but if you look at the quantum mechanics, that's one way of saying, well, these equations look like little waves traveling around. So in Feynman's interpretation, and this was just an interpretation at first, he said what's really going on here is you have an electron. An electron is surrounded by things he called virtual photons, because photons are electromagnetic waves. Virtual because these didn't behave like ordinary electric waves. It's just that it looked quantum mechanically very, very similar. They were weird because these virtual photons, it turned out, for example, were not massless. They had rest mass. So they weren't really photons. But in quantum mechanics, if you looked at it, they looked like photons that had mass, except they were there, they were sort of traveling around, and they surrounded this electron with these things. Sometimes they'd be absorbed by the electron, sometimes they'd be emitted. They wouldn't last very long. They were only in the vicinity. They never went very far. This little wave would come out, and the wave had some extent, because waves aren't localized. So it would come out, but some of it was still where the electron was, so it could be reabsorbed. I mean, here's this little electron, and it emits this wave that starts moving, and then the wave's absorbed again. It's called the emission and absorption of virtual photons. This was Feynman's way of looking at the quantum mechanics, but it made real sense to him. And then he imagined this thing emits a wave, and instead of it being reabsorbed by the original electron, it's absorbed by this. And that would transfer some momentum to this one. It would give a push on it. You're actually, something's emitted here, and it's absorbed here, and as a result, this gets pushed away. Interestingly, if you have an electron and a proton, this thing can emit a wave, and the wave may be big. It's going in this direction, and this big wave moving in this direction, because it's so big, even though it's emitted by this electron, it's big, and it's going in this direction, it could be absorbed by this one and pull the proton to it. And the numbers all worked out. So Feynman's approach was, maybe this is more fundamental than the equations of quantum mechanics. Maybe if I need to understand the behavior of fields, I should start from this approach and think of these virtual particles surrounding it, and that those virtual particles are really responsible for the forces we see in between things. This is what is called an exchange force. And in physics today, when you think in terms of the most fundamental issues of quantum mechanics, when you're trying to understand all forces from a truly fundamental point of view, a physicist such as me believes that the most fundamental way, the way that you'll get the right answer quickest, the way that you'll make the fewest mistakes, the way where you'll take into account all the subtleties of quantum mechanics, the way that when you do it this way, you really get the answers that you get from experiment. The only way you get answers from experiment is to think of all forces as being exchange forces. So when you say a force between two charged particles is actually a photon being exchanged between them, that's what we mean. That this electron by itself is surrounded by a cloud of virtual photons that behave like photons, except they behave like photons that have mass, and they're continually being emitted and absorbed, so energy is conserved. But if you put something near enough, then one of them may be absorbed on the other particle. That results in transferring some velocity to that particle. That's basically a force. And now every force in physics is that way. Gravity. I talked earlier about the gravitational field around a mass, around a black hole. In modern physics, we believe, this one is less proven than the other things I've said. I mean, the fact that the virtual photon theory is the only way to account for all the subtle measurements that can be made. No other theory succeeds in doing that. Unless you use the virtual photon theory of Feynman, called quantum electrodynamics, you wind up getting answers that differ with experiments. So in that sense, the Feynman theory is established for electromagnetism. It's also been established for the strong force and for the weak force. But it hasn't really been established for gravity. Almost everybody believes it's true for gravity too, and that may be, actually, in my mind, the most fundamental mistake that scientists are making today in their theoretical investigations of gravity. They assume that because this has worked so well with the other forces that this one must be similar. The reason it must be similar is they don't know why it should be different. If it is similar, then there's a name given to the particles. You have a mass here, and what used to be called the gravity field is now considered a sort of a soup of virtual gravity particles called gravitons. And that's what a graviton is. Now, in the classical theory of a gravitational field, if you shake a gravitational field, you should create a gravitational wave. And gravitational waves have been detected. Actually haven't been absorbed and detected, but we can tell that they're being emitted because there's some stars out there that are moving so fast, and yet they're slowing down, and you calculate how much they should be slowing down based on the waves they should be emitting, and it's a perfect match. So based on this, we know that things do emit gravitational waves. Are those gravitational waves quantized? I told you earlier in this course that all waves are quantized. Well, that is the current belief, and I'd like you on exams to state that. I'm not going to ask you for an essay question on this, but I would like you to know that there's no evidence that gravity is quantized. Everybody thinks it is, but if you really want to be out of the box, you really have to question even that. Maybe gravity is different. Waves are emitted, but maybe they're not quantized. We don't know. They're so weak that it's very hard to tell. And people have been attempting to design experiments to do this, but there's no real success in that. So that's the gravity field. Let me tell you about the strong field. Now, do you remember what the strong field is? They're the protons in the nucleus. Uranium has 92 of them. And they're really close to each other. I mean, the nucleus is so much tinier than the atom. It's 10 to the 5th times smaller. An atom is 10 to the minus 8 centimeters. The nucleus is 10 to the minus 13 centimeters. It's like that mosquito in the football field. These things are really close to each other. And yet they're all protons, so they repel each other enormously. What holds them together? We call it the nuclear force. And even worse is the individual proton. We look at a proton, we now discovered it's made up of three things. There are actually some other things in there too, but three major things that we call quarks. And you need to know that a proton has three quarks. Why do you need to know it? For the final exam, not for being a future president. And we can actually go inside of the proton. We can send electrons in and measure the charge of these quarks. And in the proton, it's really weird. This one has 2/3 of a proton charge. This has 2/3 of a proton charge. This one has minus 1/3 of a proton charge. You add those together, you get one proton charge. That's really strange. Why? Because we've never seen anything that has a charge that isn't a multiple of the proton charge, or electron, which is a negative proton charge. Charge is quantized. Quantized for a charge means multiples of the proton charge, some of the negative of a proton's charge, okay, which turns out to be 1.6 times 10 to the minus 19th coulombs, a number you don't have to know. At least that's what it used to mean. Now we have these things that are a fraction of it. Though we've actually never seen one separated. I'm going to explain why we think that's the case in a moment. And so now the current belief is that all charge is a quantized, not multiples of the proton charge, no, multiples of the quark charge, which is 1/3 times 1.6 times 10 to the minus 19th coulombs. Actually, I shouldn't cross that out, because we have a schizophrenia here. It seems that all charge that we can observe by itself, all isolated charge, is multiples of the proton charge, and confined charge inside of the proton can appear as multiples of the quark charge. But that we cannot take an individual quark and separate it out and have here a separate quark. Actually, there have been so many people looking for quarks. I mean, this is one of those obvious instant Nobel Prizes if you discover a separate quark. And there have been reports of quarks which then didn't hold up upon closer examination. So nobody got that instant Nobel. People keep on searching. They look for, well, why didn't we find it before? What's different? Where can we look where more energetic things have hit than ever before? Ah, lunar soil. Why is that? The lunar soil is on the surface. It's been exposed to high-energy cosmic rays for a long time. There's no atmosphere to protect it. Big collisions. If you're going to make a quark, that's a good place to make it. It's been out there for 4 billion years. Let's get some of that stuff and search in it for quarks. And there have been some very ingenious searches to do that, and they found no quarks. Well, or some of them found quarks, but then it turned out to be wrong. So why are there no quarks? This comes back to the exchange force. So now I'm going to talk a little bit about the deep inside nuclear physics and what is going on, and how are the quarks hidden in this way. So, let me do that here. Not there. Maybe here. Here? Yes. So here is our current understanding. We knock electrons off these things. We measure the force. There's a surprising thing about the force between the quarks. It's really unlike most other forces. You know, with the gravity, we said it's an inverse square law. You get twice as far away, and the force is 1/4. You get 3 times as far away, it's 1/9. You go 4 times as far away, it's 1/16. That seems sort of natural. As you get further away, you don't feel the force anymore. Electric charge behaves the same way. It seems almost natural. It behaves the same way. You know, you go twice as far away, the force is 1/4. 3 times as far away, the force is 1/9. 4 times as far away, the force is 1/16. Hey, we're on a roll here. What's going on with the nuclear force? Well, the force between protons is a little bit more complicated. I'm going to skip over that to get right to the force between the quarks. And here's the odd thing about the force between the quarks. As near as we can tell, the force between quarks does not get weaker as you pull them further apart. In fact, one estimate is that the strength remains identical. No matter how far apart they are, the force is the same. That means if you want to remove these quarks, you pull on them, and you pull on them, and you pull on them, and you pull on them. But never do you just pull on them. It's always pull on them. It's just it's hard. Finally, you put so much energy into doing this that you put enough energy to create 2 more quarks. I want to go over this. The result is that this quark you're pulling out suddenly has a second quark alongside of it. You've created a new quark, and now what you have is a quark pair. You don't have the individual quark. This process, which I didn't explain well enough for you to understand yet, so don't worry about that, is what we call confinement. And it's a consequence of the fact that the force has this peculiar behavior. But ironically, we can now understand that behavior in terms of exchange forces. So I'm going to give you something that isn't proven to be right, but is accepted by many people working in this field as very likely true. And someday we hope, I mean, this could be true. It's the only explanation we have, so if it turns out not to be true, we got to start over. But let me explain how that works. And it'll introduce a few new names you have heard of, but maybe didn't understand the context of it. If you take a single quark all by itself, it'll turn out to be impossible, but let's start with that. And it has a charge, which is maybe 2/3 of a proton charge. And yes, it has a charge, and therefore it's surrounded by these photons, these virtual photons. That's the electromagnetic force. But that's not important here. What's going to be important is the other force. It has a nuclear charge. It has a strong force, which is separate from the electric force. This is the force that eventually will hold the proton together and actually hold the nucleus together. So there's the strong force. The strong force you could think of as a field. That would be a classical way of doing it. But now let's think quantum mechanically. That field actually consists of a large number of virtual particles, little waves. Well, they're not little. The waves can actually be very big, but there'll be many of them, and they'll be continuously absorbed and emitted by this particle. That's the basically Feynman approach. These little waves in the modern theory, which is called quantum chromodynamics, by the way, quantum chromodynamics in nuclear forces, as near as we can tell, has nothing wrong with it. There's never been an experiment that violates it, and it makes lots of predictions. So the theory of the strong forces is pretty well worked out. But it has that weird name, quantum chromodynamics. The chromo derives from these little things. They have their own name. It used to be, I don't know, hundreds of years ago, well, 50 years ago, people who got their PhD in physics were required by their liberal arts colleges to study Greek and Latin. And as a result, they came up with Greek and Latin terms. There are still some extremely overeducated people like Murray Gell-Mann who makes contributions to this field. And when he does, he's very literary. And so he came up with the idea of naming these things, which he predicted. He called them quarks. And it comes from James Joyce. I don't know how many of you have read Finnegan's Wake multiple times and remember everything in it. Some people really love James Joyce. I'm not one of them. I've tried. Anyway, at one point in Finnegan's Wake, a character says, 3 quarks for a muster mark. And Professor Gell-Mann said, oh, that's just the word I need for these particles I'm suggesting. Another name that was suggested by someone else was they would call them aces, and that didn't catch on. The word quark was so lovely. So they were called quarks. But not all physicists are that imaginative. Not that many are literate, and they don't study Greek or Latin. So what did they call these little waves? You may be guessing, if you've heard the term. They are given the wonderful name of gluons. So what are gluons? They're the nuclear glue. They're the little waves that are constantly being emitted and absorbed by the quark that hold the nucleus together. That's what a gluon is. It's the little particle wave that is emitted in a virtual way by the quark, because the quark has a nuclear charge. I'm not talking about electric charge, nuclear charge. And so there's this field of gluons around it. And you think if you get far away, there wouldn't be very many gluons, and that in fact, therefore, if you got far away, the force would be weak. And indeed it is. But why, when you take two quarks and pull them apart, does the force remain strong? Interesting answer. The gluons, according to this theory, in order to work out right, unlike the photons, see, here you have the electric, this is gravity here, the photon fields, which I drew over here, I guess, have these virtual photons. The virtual photons don't have any charge. Electrons have charge. The waves are in charge, the electromagnetic waves. An electromagnetic wave doesn't have charge. The electron has the charge. It turns out the gluons contain the nuclear charge. They are charged waves. Now look what happens here. If you have a particle here which is, let's say, 2/3, and you have another particle here which is minus 2/3, a quark with opposite charge, it's called an antiquark, and there are these gluons coming off, and then it turns out these have gluons, and so the gluons get emitted here and absorbed here, emitted here and absorbed here. But now there's an additional thing that happens. Because the gluons are charged, they attract each other. So there's a force between the gluons, and as you pull this thing further and further away, you wind up developing this structure of attracted gluons between them. And so the force is like a rubber band. The force here remains the same no matter how far you pull it apart, because the gluons don't spread out. The gluons make this little thing that has sometimes been called a string. But be careful of the word string. In string theory, strings have three different meanings. A string is, the quark might be a string itself. There's something called a cosmic string, which is due to a gravitational behavior in general relativity theory. And then the force field of the gluons makes a string. And those are things that physicists have to keep straight. When you hear string theory, this isn't the string of the string theory. The string theory has to do with what is the actual nature of this quark at the end. So we'll come to that. Now, with this thing, as you pull it like this, you find because these things have charge, what is the name of the charge? We don't call it the nuclear charge anymore. Again, a bunch of unimaginative physicists decide it's actually not such a bad name. What they call it is the color charge. It's given the name color. And the reason it's given the name color is it turns out there are these big forces that you get, and unless you have three different colors, you will create more particles. Everything such as a proton has to be color neutral. It has to have an equal amount of all three colors. This is, I mean, the reason the word color was chosen is that people said 3 different colors. What analogy can we make? Well, white light consists of 3 colors. And you have equal amounts of all 3 colors, then you say there's no color. There are 2 ways you can do it. You could have red and anti-red, that's no color. You could have blue and anti-blue, that's no color. You can have green and anti-green, that's no color. Or you could have red, white, and green together. Red, yellow, and red, green, and blue together. And then you have white, and that's no color. And these are the same rules followed by the quarks. So, here is the bottom line. We say there are 3 kinds of nuclear charge. They are given the name, by analogy only, of red, green, and blue. Because of the way they interact, any particle that we can actually observe has to have 0 net color. And that can happen either by having a particle and antiparticle. And quark-antiquark, that's a common kind of particle, called a meson. Or you can have a particle like a proton that has an equal amount of red, green, and blue, and then it's colorless by analogy. This is just a way of remembering the rules. And that's why this is called the color force. And you will see that. It has nothing to do with color other than as an analogy to what you already know about the way the human eye works. And that's what gives rise to the name quantum chromodynamics. Dynamics means, how things behave when you put forces on them, when you interact them. That's the dynamics. The dynamical theory means theory of motion. Quantum means that these things are following the rules of quantum mechanics. These are little waves that are particle waves, and they're quantized, and they have the energy equal to h times the frequency, and they satisfy all the rules of quantum mechanics. We don't know if that'll be true for gravity, but it's true in this theory, and this theory really works. And it's called chromodynamics because the name of the force is the color force, named in analogy to the behavior of the human eye. And that's where the word comes from, and that's all it is. With the color force, it turns out if you take these two particles apart from each other, that the gluons, which carry the color force, they are the little particle waves that are virtually emitted and are responsible for the strong field. These little particles attract each other. So when you have two particles and there's a force between them, you start pulling them apart, because they attract each other, the force gets really tight, and it looks like a long string or rubber band between them. And the result is the force gets bigger and bigger. Suppose you try to pull them really apart. Then there's a huge amount of energy. Here we have one particle, which is, let's say, a 1/3 quark, and here we have a minus 1/3 quark. Put those together, and you get something called a pi meson, a particle that I have actually used in the lab for my studies. I've studied it extensively in the laboratory. You take this and you separate them, and you wind up getting this enormous, strong field between them. And the energy keeps on going up and up and up because you keep on doing work to separate them. And the amount of work it takes is an infinite amount of work if you get them infinitely far apart, because this thing never goes away. It's like a string that you're stretching, and the string is getting infinitely long. And at some point, there's enough energy in this that the string can actually break. And when it breaks, what happens is you produce pair production. You produce a particle and antiparticle. What you'll do is produce over here a minus 1/3, and over here a plus 1/3. And what you've done in trying to separate the meson is it goes bang, and you wind up getting two mesons held together. In a way, it's a little bit like magnets. If you take a magnet with a north pole and a south pole, and you break it, this isn't a monopole and that's a monopole. No, instead it's a whole bunch of dipoles all lined up. And so when you break it, you wind up getting two complete magnets. And the same thing is true. If you try to take a meson and rip it apart, you're finding you're putting more and more energy into it. Finally, you put in so much energy that there's excess energy left over to create a particle and antiparticle. At that point, the bond will break. It'll be energetically favorable to form two mesons. What you wind up doing is taking a meson, putting huge force on it, and you wind up creating another meson. You now have two mesons where you had one. And that's what happens. And that's observed. The question for a long time has been, why does that happen? And now we think it's because of this quantum chromodynamics and the force between the photons. You've gotten an earful so far. We have 15 minutes to go. Covered a lot of material. Not really adequately covered in the textbook. You may want to listen to this mostly for your own use. The amount of actual material you really have to know here is not that much. One aspect of these quarks, by the way, is when they get really close to each other, you don't have so much force. When they're really close, the gluons kind of spread out. And so within the nucleus, the quarks are pretty much free. They move around real nicely. It's only if you start pulling them out that they wind up getting this big force. So that has a name, too, in particle physics. Okay? You don't have to know this. It's called asymptotic freedom. Why asymptotic freedom? Well, if you go to the limit where they're inside the quark, they really are free. They're free like a prisoner in San Quentin is free. Free to move 3 or 4 feet and move around. But if you try to get past the walls, you're stopped. So they're confined. It's called asymptotic freedom because the way you measure it at very small distances by going to very small wavelength. That requires very high energy, which is the asymptotic end. But you don't need to know that. I'm giving you these words to give you some guidance in case you wind up reading more about this stuff, that you will have heard it. And I'm trying to be absolutely precise about everything I say so I won't mislead you at all. But this is quarks. And one of the more fascinating aspects of quarks and of understanding the subnucleus is the fact that we now think it plays these behaviors have a major role in the explosion of the universe we call the Big Bang. Question?
Why do quarks only seem to polarize the positive? Don't you have negative two-thirds, negative two-thirds, and positive third?
Okay, the question is, why do we only have positive quarks and not negative quarks? Actually, antiproton, discovered by Owen Chamberlain, who just died a few weeks ago, there was a memorial service for him. The antiquark consists of a minus two-thirds, a minus two-thirds, and a plus one-third. This is the antiproton. You know what quarks and electron consists of? None. Electrons don't seem to be made out of quarks. Electrons are made out of a particle whose name you already know. It's called the electron. An electron is an electron. We think an electron may actually be one of the fundamental particles. We think the quarks may be the fundamental particles. We fooled ourselves in this in the past, so there are these old theories that quarks are made up out of other things. Right now, there's no evidence for that. And it's possible that the electron is fundamental, that the quark is fundamental. String theory is the theory that there is basically only one kind of fundamental particle called a string. And if a string is configured in a certain way and oscillating in a certain way, we call it a quark. If it's oscillating in a different way, it's called an electron. There's some possibility that one can turn from one into the other, in which case quarks really can disappear. Protons may be able to decay. That is, you have a proton consisting of three quarks. You think it lasts forever. Well, they seem to. There have been some very good experiments that they're not really radioactive. If they were radioactive with a half-life of 100 trillion years, would we know it? Well, gee, that's a long time. The universe has only been around for, whole universe, for 14 billion years. So if they have a half-life of 100 trillion years, we certainly wouldn't see them decaying. Well, maybe we would. If you took 100 trillion protons, put them all together, then in 1 year you'd expect one to decay. Even though they have such a long half-life, you would see some of them decay. According to string theory, this should happen, but very slowly. So people have done these experiments. They take 100 trillion, bigger numbers, big tanks nearly the size of this room, and they fill them with protons, water or cleaning fluid or something like that. Any nucleus will do. And then you wait to see if that proton decays, and you have to be able to detect that one radioactive decay and see if it comes from a proton. And so far, the experiments have not detected anything. But in principle, even with a trillion-year half-life, you might be able to detect that. And according to string theory, it should happen, but nobody can predict exactly how fast. But string theory says that all these particles are really the same. They consist of little particles. They're not individual points, but they're little extended things we call strings. Now, it's not quite so simple as that, because in order to make string theory work, it turns out you have to assume that there are some hidden dimensions. I mean, there's up, down, and sideways. But there's yet another dimension. I don't mean time. I mean a real spatial dimension. It's that way, which I can't point to because you can't see in that direction. And these dimensions don't affect our lives because they're confined. That means they actually go in little circles. So you can't go very far in those dimensions. But when you get down to really tiny things, then they make a big difference. And there are some people who are looking for such strings now because in gravity, it's conceivable that these extra dimensions actually, until a few years ago, maybe at 1 centimeter, there are extra dimensions that only gravity behaves in. And down to 1 millimeter, people have looked now. I'm not explaining this in a way that you could possibly follow what I'm saying. But in string theory, they have to introduce typically 11 dimensions, all of which are confined, which means they're wrapped up, and so you don't experience them in everyday life. Just as if you had if an ant were living on a tube, If he were really tiny, he'd say, oh, there are two dimensions. You go around this way and you go that way, and I can move all around. But if the larger animal were living on that tube, there's the big bug, he would only know about up and down. This other dimension is so small and circular that he's not aware of it. And this is the idea in string theory. The string theory does seem to at least be self-consistent. I don't want to say it works, because it doesn't predict anything yet. Well, it actually does predict lots of things, and all those predictions turn out to be false, and therefore they had to modify the string theory in order to keep these things from being false, and they were able to do that. So I don't want to say it never predicted anything. It did, but they were wrong. I'm not a great enthusiast for string theory. But you could at least make a self-consistent theory that strings that exist, they have to exist at 11 dimensions. All of them except 3 space and 1 time is confined. That is, it's all hidden. And then you could put together a self-consistent theory in which the electron and the proton, the quark, are actually 2 aspects of the same string. And so that's a proud mathematical achievement. What we don't know is whether it has any relationship to reality. It might. A lot of people are working on it very hard. So that's what string theory is. But one of the real surprises in all of this is the effect it has on our understanding of the universe. So we're going to wind up this course now by going into what is the universe, what is it made up of, and how does all this somehow explain, or at least tell us about, the creation of the universe. So I'm going to spend my last 5 minutes giving you a little bit of an introduction to this. Here's something I want you to ponder. First thing is, reading is due on Thursday as usual, last chapter, on the universe. I showed you these galaxies up there, and we're looking at the Andromeda galaxy. Suppose you look beyond. Do you find other galaxies? Yes, you do. How many stars are in our galaxy? About 10 billion. How many galaxies can we see with the powerful telescopes? I'll show a photo next time. The answer is, well, you can't look everywhere because there are too many little spots to look. So you look at a few little regions and count the number of galaxies, and you look there like I'd suggested for the stars. And when you do this, what you discover is the answer for the number of galaxies that we could photograph if we took the time is greater than 100 billion. In other words, we can observe out there more galaxies than we can observe stars within our own galaxy. And these galaxies typically have as many stars as our own galaxy. As Carl Sagan would have said, there are billions and billions. And by the way, his series I guess has been put back on. Really a wonderful series. Carl, by the way, of all people who have worked in popularizing science, in writing science fiction, there are some people who just kind of don't pay much attention to the facts. Some of the most popular science fiction writers don't bother to check their facts. Even my own theories, which have worked their way into science fiction, have been completely distorted when they were put in. But there is one person who has been very, very careful, and that's Carl Sagan. And by far the best books on popular science you can get are Sagan's books. I really recommend that. Almost nobody else is really in his class in terms of being able. This is Carl Sagan. He passed away, 10 years ago. And he was so effective at popularizing science while keeping the accuracy of everything he said. Some of my treasured books are books that he sent me with nice little statements on them in which he described my theories, and he got them right. Okay, so I'm a real fan of Carl Sagan. And his Cosmos series, which is being rebroadcast, is wonderful, although people make fun of him for saying, yeah, there's lots of space out there, billions and billions. Some people say that we should introduce the unit of a number, a new number. You know, we have a million, billion, trillion, and there should be the unit called the Sagan, which is billions and billions. Anyway, I'm a real fan of Carl Sagan's work, and he talked about all of this stuff. And there are more galaxies out there than there are stars within our own galaxy. Now, here's the weird part. Hubble, in the 1930s, He's lately been made famous by the fact that our best space telescope was named after him. And it is a suitable honor because he started studying these galaxies. He made two discoveries about them. One is that they were galaxies. People didn't even know they were so far away. You know, it's actually very hard to tell how far away things are. Look at the Golden Gate Bridge and look at the moon. And look at them and say, which one is closer? And it's not so easy to tell. Well, you can go to the Golden Gate, right? But if you look at the moon and you look at the stars, which one is closer? That's not so obvious until the moon comes in front of the stars. And you say, I know which one is closer. The galaxies and the stars, which ones are closer? Well, people thought the galaxies were just big clumps of dust that were, and gas that were as close as the stars. It turns out they're not. The galaxies are separate groups of stars much further away than any stars within our own galaxy. Hubble discovered that. He discovered that by getting a good enough telescope to be able to see the individual stars within these galaxies and recognize them as similar stars to ones in our own galaxy, but they were so much dimmer they must be further away. So he discovered that these are galaxies. And secondly, when he looked at these galaxies, he was able to measure their velocity to us or for us by using the Doppler shift. Remember the Doppler shift? The Doppler shift is the fact that when I'm moving towards you, my voice seems to be higher. And when I'm moving away from you, the voice seems to be lower. And the reason is, as I'm coming close to you, every wave I emit comes to you a little bit faster. So the frequencies are higher. And when I'm moving away, they have to go further, so it seems lower. And that's the Doppler shift. Same thing is true of light. He measured the Doppler shift of the spectral lines. The fact that atoms have spectral lines is their spectral fingerprint. That's quantum mechanics. If those spectral lines come up at the wrong frequency, it moves the galaxy is moving towards you or away from you. What Hubble discovered was that as you looked at these billions and billions of galaxies, they almost all, with a couple exceptions, but almost all of them are moving away from us. That's Hubble's law, and we'll talk about that on Thursday.